Very welcome to this webinar, and we are very happy to have you all with us today from all around the world. Today we'll dive in something quite small but mighty, okay, magnesium. I'm working with it every day since 5 years, and I realize that there is always new things to learn about this mineral. So as you may know, magnesium is involved in more than 300 enzymatic reactions in the body. Okay, so from the neuromuscular function to the energy metabolism, magnesium is a bit everywhere. For the ruminants, but also for us, humans. And when we talk about our lactating cows, it's a key element to support the rumen stability, the stress resistance, and the overall productivity. So today we start this discussion with a presentation from Dr. Alex BACH, who is a dairy production researcher in Spain and also professor at the Catalan Institute Research and Advanced Studies. So he will go in more details regarding the magnesium absorption, regulation, the interaction with other minerals also, and how magnesium is important and its important role in the organism. Then I will talk more about magnesium salts, the interest of magnesium oxide, and also we will talk about the specificities of the product pHix-up, which is an innovative magnesium oxide blend with an aim to be more than just a simple supply of magnesium. So I hope everybody is ready to learn more about magnesium, and Alex, the floor is yours.
Well, thank you very much, Melody, for the introduction. It's a real pleasure to be with you guys here today. I'm going to start sharing the screen. Today, I will be talking about magnesium. As Melody was saying, I will try to link it to health and productivity in dairy cows. I warned you, it's a little bit technical. I go deep into how magnesium operates, how it is absorbed, and then I go from there to what is it good for the cow and what can we see from outside world, right? So I will start just pointing out that magnesium is very, very similar to calcium. So they are in the periodic table, they are really, very close. So they're very similar elements, but they're very distinct. Their function in their body is very, very different. And I'll tell you why that's the case. Yeah? Just before we get into cows, just a little, I don't know, curiosity about magnesium. It's a metal, okay, as you know. So it's if we go back here, this is the metals, right? It's a metal that actually burns. Okay, so it's a metal that burns, and it's been used back in the old days. The guys that are old like me will remember we had photo machines with flash, and the flash was actually magnesium, and that spark and that light was coming by burning magnesium. Okay, of course we're not doing that in the dairy cows, but I just thought that's an interesting curiosity because it's the only metal that actually burns. So now going back to the difference I was saying between magnesium and the other elements in the periodic table that are positively charged with two charges like calcium, potassium, or sodium, is that it really attracts a lot more water. Okay, so when we look at the magnesium molecule that will be here, it's surrounded by 400 times more water than it would be calcium or sodium even. So, and that's what makes it very different, and that's why it operates so differently in biology. Calcium is able to go through several membranes because it's much smaller. It also takes much less energy to release the water that's surrounding it, whereas magnesium has a lot of water. It takes a lot of energy to get rid of it, and is so big that it doesn't flow through the membranes. Okay, so that's important for muscular tone, for nerve transmission, and also very enzymatic reactions where the size of the enzyme and the protein, it's very important. So that's why magnesium is so unique in that sense. Other characteristic about magnesium, while it's found mainly in our bodies in the bone, so it's as calcium is located in the bone, the difference between calcium and magnesium in the bone, partly due to the water content of magnesium, is that the body cannot subtract magnesium from the bone. Okay, so we have the osteoclast that will release calcium into the circulation when the animal needs calcium. The cows and us, we cannot do that. So the magnesium that's deposited in the bone stays in the bone. Then we also find magnesium in soft tissue, basically the muscle, and also in other soft tissues like the intestines and the rest of the viscera. Okay, 20%. How much magnesium we have in blood? Well, it oscillates a lot. The reason why it oscillates a lot is because mainly the concentrations in blood, which range between 1.9 and 2.4 milligrams per deciliter, are not controlled. Okay, it's probably one of the few macrominerals that is not controlled in terms of concentrations in blood. So we have control for potassium, we have control for sodium, for calcium, not for magnesium. Okay, so the difference between these two, 1.9, 2.4, or sometimes it's even 0.7 or whatever, right? It's basically how much magnesium is the animal eating. If the animal eats enough, then you're going to go up to 2.4, and any excess will be excreted in urine. When the animal starts eating insufficient amounts, then this concentration starts declining, and it can go to as low as 1.5, 1.6, and then it's going to cause some pathology, as I'll explain later. Okay. As Melanie was saying, magnesium is a big player in almost any reaction in our body. It plays a role in many enzymes as a cofactor, and it's vital for muscle contraction, for nerve conduction, and of course bones. When we look at the list, I can make a huge list. I think Melanie said it, there's more than 300 enzymes where magnesium plays a role, but we have a lot of kinases. So these are involved in energy production. ATPases also involved in energy production, so you can already start establishing the link between magnesium and milk production. And then there's a whole number of functions where these enzymes play their action. So that would be in several proteins, in ribosomes, in muscle contraction, in cell adhesion, you name it. Almost any single reaction in the body at some point will have a dependence on magnesium. It's not only in our body or in the body of the cow, it's also for the microbes. So there are some microbes, not all of them, but as you know, they have cellulases. And these cellulases are, of course, in the membrane outside the bacteria. That's why they attach to the fiber, that they break down the fiber, and then that small molecules of glucose and get imported inside the cell. So some of these cellulases, they have magnesium as cofactors. Okay, so they actually need magnesium. So we not only need magnesium for the cow, we also need magnesium for proper fiber degradation in the rumen. Magnesium is also pivotal for acetyl-CoA carboxylase, which is an enzyme that participates in milk fat synthesis. So you may have a problem with milk fat if you have low magnesium in your diet. It is true that in this case, this acetyl-CoA carboxylase can actually use magnesium or manganese as a cofactor. Okay, but chances are that if you have a deficiency of magnesium, you also have a deficiency of manganese. Manganese is a micromineral. It's always in the much lower concentrations than magnesium. So it's unlikely that this will happen, but just for you to know that it could be interchanged with manganese in this case. I'll show you later, but also magnesium participates in both the activation or the formation of vitamin D3 and also its metabolism. So in its transportation in blood and its action in the target tissues. I'll explain that later. So what happens typically? Well, if we have a cow that eats maybe, I don't know, 50 grams of magnesium, okay, we're going to find in the feces around 40 grams of that. Okay, about 37 will come from the magnesium that the animal consumed, and about 3 grams will come from endogenous sources of magnesium. So the animal will be excreting magnesium into the intestine, and then that's going to go back into, part of it into the urine, part of it will go into the milk, part of it will go into the fetus. So the endogenous and the ingested, I'm talking about. These numbers we more or less know. The numbers on the left, we have no idea. Okay, we still don't know how is that available magnesium that the animal is able to absorb goes actually into the intracellular media of the cells or into the bone. We still don't know how that happens. We know it happens, but we don't know at what rate and how it's brought about. But basically the message here is that we are very inefficient If we feed 50 grams, we collect 40 in the feces, okay? And I'll explain why that is and how we can change these numbers and try to make it a bit better. Why do we need milk? Magnesium, sorry. Well, we need it for a number of things. As I said, we have plenty of enzyme reactions that need it, but also most important, in terms of dairy production, we need magnesium to produce milk. Milk has about 1 gram of calcium per kilo. In terms of magnesium, is the second most important mineral in milk, and it's 10 times less than calcium, but it's the most important one after calcium. And it has like 0.15 grams of magnesium per kilo of milk. We've been using rations that have been traditionally low in magnesium, okay? Because the old NRC and all other models that we were using for feeding cows, they did not consider how magnesium is absorbed. And I will spend a little bit of time explaining why that happens, because it's important that we understand how that happens to then understand why we need to put more magnesium in our diets. But the fact is that the new NASEM 2021 has actually increased by about 50% the amount of magnesium required for all the stages of dairy production, from calves to heifers and cows, compared with previous versions. And the main reason for this increase of 50% is because NRC 2001 and other models were assuming that the absorption coefficient for magnesium was 70% or 0.7, and now it has been reduced to anywhere between 0.25 and 0.45, depending on the source that you use. Sulfates are more digestible or more absorbable. Oxides and other forms are a little bit less. But of course, then that's the average, and it depends on the source, but it also depends on the diet and other elements, as I'll explain a bit later. So there's a lot of noise here, and that's why we need to understand if our magnesium levels in the diet are correct or not, because it's not a fixed number. It will depend on the level of milk production. The more milk I produce, the more magnesium I need. And also the diet composition will have a big influence on my absorption coefficient, and therefore the amount of magnesium that I need to add in my diet. In terms of sources, right? So we have inorganic magnesium sources. Yeah, typically that's what we add. And we also have magnesium sources in the form of forages and or other ingredients, but the amount of magnesium in forages is quite low, and other ingredients is not available as inorganic. So there's a lot of noise and uncertainty. So we basically rely on inorganic forms to provide magnesium to our animals, okay? And the most common one is magnesium oxide, which has about 60% magnesium. It depends on the source and its quality and purity. And then another one is magnesium sulfate or magnesium acetate. But these ones, even though they might have a better digestibility, they have a lower palatability, okay? This is just a nice study where they actually compare the bioavailability or the absorption of different magnesium oxide sources. And you can see that some of them have an absorption of 10%. That means that you're feeding 10 grams, you're only going to absorb 1. And some of them have 100%. So if you're feeding 10 grams, you'll achieve 10 grams of absorption. So it's important that when we include magnesium oxide in our diet, we pay attention to the source, because not all the magnesium oxides are created equal. So let's start with absorption. That's the key point. That's what's going to help us to understand whether my levels of magnesium in the diet are correct or not. And of course, we have different types of animals in the reproduction. In calves, magnesium is absorbed in the intestine, okay, as it is in the swine, in the poultry, and in humans. But as the animal matures, that absorption of magnesium in the small intestine disappears, and all the magnesium is absorbed in the rumen. Okay, once the rumen is functional, there is no absorption of magnesium in the intestine of ruminants. And that absorption occurs in the rumen via 2 mechanisms. We can have one mechanism that is high affinity, low capacity. That means that it requires little amount of magnesium for it to work, but it will move low amounts of magnesium every time. There is another one that is low affinity, so you need lots of magnesium in the rumen, high capacity, and it's able to transport that magnesium with a big quantity, okay? The difference between these two, and I'll go a bit deeper on it, is that this one, which is the main one actually, this is the main mechanism by which magnesium is absorbed,
It depends on my potassium concentrations. If there is high potassium concentrations, the absorption of magnesium is severely decreased. This one is independent of potassium, but it needs a lot of magnesium in the rumen. So we need to feed lots of magnesium for this to start working. So basically, in calves and in non-ruminant animals, magnesium can be absorbed in the intestine through these paracellular mechanisms. So between the cells in the intestine, magnesium can go through, okay? Of course, they also have the same mechanism that we have in the rumen, which is coupled to chlorine or other anions, and that will absorb also magnesium. In both cases, is always like active absorption, but it's quite easy in the intestine just to go like that. Okay, in the ruminants, that's not an option. This goes away, the expression of these transporters. So it's only expressed in the rumen. So when we try to absorb magnesium in the rumen, it's not an intestine. It's not the intestine, which is just a monolayer of cells. We have at least 3 layers in the rumen, right? So first we have the apical membrane that we need to absorb magnesium into the first layer. Then it has to go through different layers of the rumen wall, and at the end reaches the basolateral membrane, and then it goes into the blood. So we have to overcome several transactions between cells to finally reach the bloodstream. So this is a representation of basically what happens. This is the rumen. Rumen pH is about 6.5. Important for us and good is that the amount of acid that is nearby the rumen wall in close connection with the papillae is typically lower. And it's always lower than the pH in the rumen in the center. That's because in the center, there is a lot of flow. So there is water moving, there is passage rate. Here, there is water that is trapped between the papillae, and there is fermentation going on by bacteria. So there is less water being moved, there is less acid being removed. So pH is typically lower in the vicinity of the cell. When I say that is a good thing, and I'll show you later, is because magnesium is more soluble the lower the pH is. So the first thing we need for magnesium to be absorbed is that it becomes solubilized. Okay, whether we feed magnesium oxide or magnesium sulfate, we need to separate the oxide from the magnesium and the sulfate from the magnesium and just get magnesium by itself. So it needs to be solubilized. That solubilization process is more effective at low pH. So that helps us. But then the magnesium needs to go through this apical level, then go through different layers, and at the end go through the blood. Okay. So what do we have? We have 2 possible mechanisms. I'm going to start with this one, which is the main one. This is both of them are active, so that means they require energy. This one is basically dependent on the potential difference. The potential voltage inside the cell is negative, like minus 70 millivolts. Here is positive. So that helps magnesium to flow from here to there. Okay, so we need to maintain a negative millivolts here in the cells for this to work. And that is basically maintained by the sodium-potassium pump, and that's going to make magnesium inside. The problem is that if we have potassium, instead of having magnesium going in there, we're going to have some potassium getting inside the cell. That's going to increase the millivolts inside the cell. So the potential difference between the inside and the outside is going to be reduced, and magnesium is not going to be able to get inside. Okay, so that's the main problem. That's why potassium competes with magnesium absorption, not because it uses the same channel, just because it changes the voltage inside the cell. Because there is an accumulation of potassium inside, then the millivolts go up, and then the potential difference between the inside and the outside decreases. Magnesium cannot be absorbed. Okay, we can help that, and I'll show you a bit later with these pumps here. Okay, this magnesium, once it's inside the cell, it can be used for many things, right? But it will be transferred to the next one anyway. But the cell, it's able to get this potassium out with sodium-potassium pumps. For every 3 sodiums that the cell gets in, we let out 2 potassiums, okay? So that will help to depolarize the cell, okay? So if we are able to put potassium in there, we're gonna remove, if we're able to put sodium in here, we're gonna remove potassium, we're gonna reduce millivolts, and then we're gonna facilitate the absorption of magnesium again, Okay, so that's one thing that we can do, and I'll show you how that works. But that's the main concept. Okay. The second way that magnesium can be absorbed is not very common, but it's also a possibility. This is more common in the intestine of non-ruminants, but it's also present in the rumen. Is there is a co-transporter. So it's basically magnesium and an ion, typically chlorine. Okay, and these two will get inside the cell by an active transport. It's independent of potassium because it just depends on the chlorine and the magnesium. But for this to work, they just have a very low affinity. So you need to have huge concentration of magnesium for this system to work. And that's not usually the case. Okay. All right. Then the last part is, okay, we've managed to get magnesium inside the apical cell. Then we go through the different layers of rumen. And then at the end, we get into the lamina propria, and then it goes into the blood. That's where the sodium-potassium pump, again, participates. We need energy. And we have an interchange between magnesium and sodium to reach the blood. Okay, so you can already start figuring out that magnesium absorption will depend basically on chlorine, but not much because this is not a very important mechanisms. Sodium, oh yes, because we need it to remove potassium from the cell and also to move away magnesium from the cell into the blood. And potassium, because it will compete for this by being accumulation of potassium here and increasing the millivolts inside the cell. Okay, so these three main things, sodium, potassium, and to a lower term chlorine, will influence magnesium absorption. Other things that will influence magnesium absorption, the slide that I showed you before, this one here, the main reason why these guys are very absorbed and these guys are not is basically solubility. Okay, these forms are not soluble, and if the magnesium oxide is not soluble, I can guarantee you will not be absorbed. Okay, it needs to be soluble in the form of just magnesium alone before it can be absorbed. So that depends on pH, and that's the first stage for magnesium absorption. This is pH. This is the amount of magnesium that can be solubilized, and you can see that in a range between 6 and 6.5. There is a huge change in solubility of magnesium. Okay, we can talk about this later in the chat or in the questions or in another session. If you want to assess if your magnesium oxide is good quality or not, people use the acetic acid test, which is just putting vinegar in magnesium oxide and see if the pH changes. That means that there is a release of magnesium and formation of magnesium hydroxide. But of course, if you're doing that test at a pH of 2 or 4, which is the vinegar pH, everything will be solubilized. All right. The tricky thing is to get magnesium oxide solubilized at a pH that is around the rumen. Okay, so it's about 6.5 or 6.2. Here, small changes in pH will have huge changes in solubility. You're talking between 40 and 60%. Okay, so that's where you have to assess solubility at that pH range. But anyway, when we're talking about the rumen, that we're talking about this area, so just between here and here, that's where our solubility will range in the rumen for most products. Okay. All right. So what is going to influence that absorption? And that's important for you to understand, because then you have to decide when you do the ration whether your ration is adequate in magnesium or not. Okay. So things that will help you is sodium, as I said before. And the studies show that if you have insufficient amount of sodium, you might have problems with magnesium oxide. Two things happen. If you have inadequate amounts of sodium, the concentration of potassium in the rumen fluid will increase. Why is that happening? That happens because of aldosterone, and I'll talk about this in a bit, in a few slides. Okay. This is corrected by meeting the sodium requirements. Okay, that doesn't mean that the more sodium you add, the better it will be. It's just an inadequate supply is negative. An excess or a supply of sodium above the requirements has no effect. Okay, so you just need to be sure that the ration has enough sodium. Don't overdo it. Don't add more sodium thinking that it's going to help magnesium absorption, because it's not. Okay. High phosphorus concentrations will also affect magnesium absorption. I will talk about this a bit later as well. High ammonia also will influence magnesium oxide or magnesium absorption. It doesn't have to be oxide. And also addition of fats will reduce magnesium absorption. And I will explain you why all these things happen. With phosphorus, the problem with phosphorus is that magnesium will form what is called magnesium phosphates that are not absorbable. Okay, so this is just the amount of phosphorus that's available for the animal to be absorbed, and this is at low levels of magnesium and high levels of magnesium. And you see that when you add more magnesium, you have less water extracted phosphorus, which means that there is less phosphorus available, which means that the magnesium that you added is also less available because it formed these magnesium phosphates that are not absorbable. Okay, so the good thing about this is that in dairy cows we don't need to feed a lot of phosphorus. Probably 0.28% of the dry matter is more than enough because we have lots of phosphates, phosphatase, in the rumen from bacteria that are very effective getting the little pieces of phosphorus from different ingredients. So we don't need a lot of phosphorus in our diet. So that's a good thing. So these problems of high phosphorus and magnesium is not very common in dairy cows, except some people that have this belief that comes from old times that phosphorus is needed to promote better reproduction in cows, even though there is plenty of studies that show that no, you can have the same reproduction efficiency with 0.28% all the way to 0.35% phosphorus. There is no need to increase phosphorus in the ration above 0.28%. So if you do that, the interference with magnesium oxide is not a problem. Sodium, I was saying before, right? So when you have an insufficient amount of sodium in the diet, you will have an increased concentration of potassium in the rumen. Why would that be, right? Well, sodium, as many other minerals except magnesium, are controlled by hormones. And one of the hormones that controls sodium in blood is aldosterone. And whenever sodium goes down, aldosterone goes up. And that will improve the retention of potassium in the saliva and the excretion of potassium in saliva and also in urine. Okay, so the animal is trying to get rid of potassium because the ratio between potassium and sodium is key for the heart function and many other things. So if you have little sodium, you also have to have little potassium. And the way that the animal gets rid of potassium is just by sending it to the urine or sending it to the saliva and in the rumen. And of course, in the rumen will interfere with magnesium oxide. So that's why low sodium will minimize magnesium absorption. Ammonia is also a potential interference with magnesium for two reasons. One is because you will make manganate phosphates, ammonium phosphates that are totally undigestible. And also because ammonia is a base, it will increase rumen pH and will decrease the gradient, electrochemical gradient across the wall of the rumen, and also the solubility of magnesium. Okay, so it has two modes of action. This will happen when you are overfeeding protein. So if you're feeding rations with lots of protein and very little starch, you will have some ammonia formation in the rumen. If you feed lots of lash pasture or lots of forages that are fresh and little starch, you also will be accumulating ammonia. In those situations, you have to make sure that you have enough magnesium because otherwise that magnesium will be absorbed with less efficiency. With fat, as I said before, every time that you add external fat, like 2.5 or 5% added fat, the magnesium absorption decreases by 20%. This is because magnesium can form soaps very easily in the rumen. So when you start feeding fats, you will have the connection between magnesium and the fats, and you will make soaps. So you basically will have magnesium with STRH from sodium. You're going to have magnesium esterates, which is basically a soap, and that's not going to be absorbed. It will be, once the pH goes down, this will be dissociated, but that already happens in the intestine, and it's too late for this magnesium to be absorbed, so you lose it. Okay, so you have to watch the amount of fat that you're adding and the type of fat, of course, because if you're feeding inert fats that are already in the form of a soap or they are protected, this is less likely to happen. But if you're using hydrogenated fat, for instance, this will happen. Okay. Another one that I haven't mentioned, and I haven't mentioned because we don't really know what's going on, is calcium. Okay, but there is some evidence that calcium may compete with magnesium to enter through the rumen wall. Okay, using that the first mode of action that I show you, that depends, that it's sensitive to potential difference in millivolts in the cell, and it's sensitive to potassium. But this is a study where they fed 0.49, 0.93, and 136% calcium. These were transition cows. And you can see that when you fed lots of calcium, the amount of magnesium in plasma went down. Okay, and when you have intermediate calcium, you have a little bit less, and with less calcium, you have more. So we don't know why this happens. This is an hypothesis. It could be that calcium goes through the magnesium channel. We don't know. Okay, but it's an observation that it's there. All right. So that's about absorption. Now, what do we do in terms of practical approaches with magnesium? We have several situations where we have to be aware of the importance of magnesium. One is heat stress. The other one is the transition cows. Okay. And at the end, I will provide you some levels of potassium of magnesium in the diet of different animals, from calves to heifers, dry cows. But as we saw in the previous session, heat stress is very important in cows nowadays. I'm now in Barcelona. It's 37 degrees, so it's crazy. The summers that we're having and experiences in the last years. So this is a topic that is becoming more important every time. As you know, cows sweat using potassium, right? So as a good practice, that in summer we have to make sure that the cows are able to sweat, so because that's the best mechanisms to release heat. And of course, we can increase potassium in the diet, so we allow sweating, okay? And of course, when we increase potassium and we go to 1.6, 1.7, what's going to happen? We're going to reduce the amount of magnesium that is absorbed. So we have to also increase the amount of magnesium that we provide to the cows, okay? The other problem is that in heat stress, we have low aldosterone, okay? Because we have little potassium. So that's going to help the potassium that the animal has, the little one, the little potassium that it has, to stay in blood, okay? When the animal retains potassium, it also retains hydrogens. So that means that we have metabolic acidosis. Whenever you have metabolic acidosis, the animal will stop eating. This is dairy cows that were fed a bolus that was controlled. It was just nothing. And it was a bolus that contained ammonium chloride, which is, it causes metabolic acidosis. It will reduce blood pH. The day after we fed that bolus, and blood pH went down and urine pH went down, intake went down from 25.5 to 22.5. We lost 3 kilos of intake with a single bolus. And it took about 4 days for the cows to resume or reach the same intake as the cows that didn't have any bolus. So that it really illustrates what happens when you have a metabolic acidosis, as you may have when you have heat stress. Of course, when we talk about magnesium supply to the cows, it depends on the absorption of magnesium, but it also depends, on the proportion of magnesium in absorption of magnesium in the diet, or the solubility of it. But it also depends on how much diet the animal consumes. So we can say, no, my magnesium levels have to be 0.2%, but it depends. If we have cows that only eat 10 kilos, then I may need to go to 0.3%. So, and then in heat stress, we have cows that consume less, basically we have metabolic acidosis. We need to put more magnesium in the diet because we have more potassium in the diet, but we also need to put extra magnesium in the diet because the cows eat less. Okay, so everything adds up, right? That's the idea, that's why it's important that you understand how everything works, because then you can control the amounts of magnesium that you feed to your cows at different stages of production and weather. The other interesting point for magnesium is the transition, right? One common thing that we do in the transition period is to avoid hypocalcemia postpartum. And we typically do that by feeding anionic salts. We could have a debate about this. I'm not going to get into that. But basically, the mode of action of anionic salts is that they cause a metabolic acidosis. And we know that when we cause a metabolic acidosis, intake will go down. Another thing that happens when you do metabolic acidosis with anionic salts is that acid in blood will be excreted by the kidneys into the urine. When that happens, for a mechanism that we still don't know, that acid that goes out, it's accompanied by calcium. So under non-metabolic acidosis, the pH in the urine is 7.8, 8.2. The cows excrete about half a gram of calcium per day. When you induce an acidosis in blood, you remove acid in urine, so the pH goes down to 5.9, 5.8, 6.2, and the cows will excrete about 8 grams of calcium. Of course, when you remove the ammonium salts, the cow finds itself with 8 grams of calcium that prevents hypocalcemia. However, when you look at the literature, the effectiveness of this approach is very high for milk fever, okay? So clinical hypocalcemia, but it has no effect on clinical hypocalcemia, okay? Subclinical hypocalcemia. So most people use anionic salts to avoid subclinical hypocalcemia because clinicals are not very common. It's about 3-4%. So clinical is thought to be 50, 70, whatever. You cannot see it. So everything would be subclinical, right? But the fact of the matter is that it doesn't seem to be active or effective against subclinical hypocalcemia. Okay? Then if we look at magnesium, what could be the link between these anionic salts and magnesium, right? Like I said before, magnesium in blood is 1.9, 2.6, maybe 2.7, 1.7, but that's pretty much where it is. If it falls below 1.25, then the parathyroid gland, which is the one responsible for secreting PTH, parathyroid hormone, which is responsible for increasing calcium in blood by fostering vitamin D production and absorption of calcium in the intestine. If there is no PTH, then calcium in blood will go down. Okay. What happens is that magnesium, as I said before, plays a role in many things, and one of the actions where it plays is in the G proteins associated with calcium sensoring receptor. Okay, these receptors that depend on magnesium, they are the ones that sense how much calcium is in blood, and if there is little calcium in blood, then it's going to foster the release of PTH. But if there is no magnesium, these calcium sensing receptors cannot work, and they cannot know if there is calcium enough in blood, so there is no release of PTH. If we go to a magnesium below 1.7, we can also alter the responsiveness of the tissues. So now we're going to have a situation where PTH is not released because the calcium sensing receptors are not sensing that there is low pH, low calcium. And on the other side, the little PTH that is actually released is not interacting with the target tissues. So it's not interacting with the liver to produce vitamin D or with the kidney, and is not interacting with the intestine to absorb calcium. Okay. There is an interesting meta-analysis where they actually reported that an increase in dietary magnesium concentrations from 0.3 to 0.4, so just 0.1% increase, was resulted in approximately 62% decrease in milk fever risk. Okay, so if you put in a scale, okay, I want to use anionic salts or I want to use a magnesium, that in the transition period, if I look at the meta-analysis on anionic salts, the reduction is about almost nothing. That would be 1.5%. In this case, yes, in this case it's about 10%. Okay, from 16 to 3. Here we're talking about 62%. Okay, so it might actually be that the effect of magnesium is more powerful than the effect of anionic salts on clinical hypocalcemia. Okay, and on top of that, when we look at the studies involving anionic salts, most of the anionic salt sources, they use magnesium sulfate or magnesium chloride. Both of them have magnesium. Okay, so then the question comes: is the results we see with anionic salts on hypocalcemia the result of the sulfates and the chlorines, which will reduce pH, or is the effect of magnesium? Or it could be both. We don't know. Okay. It's interesting to see that primiparous cows have lower magnesium, greater magnesium concentrations than multiparous cows. And you all know that primiparous cows that have more magnesium in blood have less chances of incurring hypocalcemia. Okay, People always said that now it's because their bone is more flexible, is more able, they're still growing. It could be, but it could also be that they just have less hypocalcemia because they have more magnesium. Another problem with magnesium and importance in the dry period is that cows tend to have a much greater pH in the rumen, which means that the magnesium that is solubilized is lower. So that means that chances are that we might have a deficiency of magnesium during the transition period, and that might be causing some problems with calcium after calving, okay? Because remember that if we have high pH, we'll have high pH because the rations for the dry period are high in forages. High pH means low solubility of magnesium. That means low absorption, okay? There is an interesting study providing some evidence for what I was saying about the importance, the potential importance of magnesium during the transition period. This is cows that had low magnesium in blood or high magnesium. Low was between 145 and 26. High was 2754. That's a lot of magnesium, okay? That's very, very high. But what you see is that cows that had high magnesium, they have almost half incidence of dystocia, pretty much the same retained placenta, pretty much the same metritis, half endometritis. Metabolic disorders were the same. Digestive mastitis was a bit lower. Lameness, 5 times less. And the culling rate was a little bit lower, but not different. Okay, but there are big changes in endometritis, for instance, which is a proxy for hypocalcemia, if you wish. Okay, so it provides some interesting data. Then, when we look at the number of animals that actually remain in the herd at 210 days, no, sorry, this is the days to pregnancy. This is the reproductive success of the animals. Animals that had high magnesium, okay, they conceived much earlier. Okay, so by 210 days of lactation, you had close to, that would be 50, 70 animals were pregnant. Okay, all this. Whereas animals with low magnesium, they had about only 40% of the animals were pregnant by 210 days. Okay, whether this is for better calcium metabolism or for less endometritis or a combination of both, we don't know, but this is observational studies providing some support for being generous with the amount of magnesium that we feed during the transition. Okay, getting to the end. In humans and in rats, low magnesium results in lower serum concentration of vitamin D. I said it before. Why is that? Well, for a number of reasons, but as I said before, magnesium is a cofactor of many enzymes. The beta hydroxylase, which is the first step for activation of vitamin D3 in the liver. Then we have the alpha hydroxylase, which also activates the vitamin D2 into D3 in the kidney. So all these steps where we are actually activating vitamin D3 and also the vitamin D binding protein, which will carry out the provitamin D into the blood to reach the kidney, is also influenced by magnesium. And of course, we have PTH that is also influenced by magnesium. And PTH also fosters the hydroxylation of vitamin D3 or the activation of vitamin D3. So we have no PTH, we have no binding protein for vitamin D, we have little activity of the enzymes, vitamin D goes down, calcium absorption goes down. Right? So you're going to start seeing the importance of magnesium in the calcium metabolism. So why should we feed magnesium before calving? Well, it will facilitate fiber digestion of rations that are very high in fiber, typically fat during the dry period. Will improve PTH activity, hopefully reducing hypocalcemia, and will improve vitamin D functionality, also improving hypocalcemia. Post-calving is the same thing. It will improve fiber digestion, will improve vitamin D3, and also we have an additional one, which we'll talk about it in the next webinar, which it will improve rumen conditions, because magnesium is not only an element that is vital for the cow, it also has an action as a rumen buffer. So we've been talking about the needs of magnesium, but how about if we have not enough magnesium in the diet? Then we're going to have hypomagnesemia. And that typically it's illustrated by tremor or agitation, fasciculation. This is just jittering of the muscles, like tickling all the time. There is depression, there is arrhythmia in the heart, so the nerve and the muscle functions don't work properly. Also, when magnesium levels are low, calcium channels in the kidney, they will not work either. Okay, so then we're going to lose also potassium in the urine, and that may cause a threatening problem for the animal. If we deplete potassium, the heart stops pumping and the animal dies. This is very typical in animals on pasture. It's not typical in dairy cows in intensive production. We will talk about this in a later webinar, so I'm just going to go a bit fast about this. But basically, when you have cows that eat lots of grass, little concentrates, these grass are high in potassium. You have high pH in the rumen, low solubility of magnesium, lots of potassium, little absorption of magnesium. So you have all the ingredients for the cow to start having problems having magnesium, and then you have grass tetany or hypomagnesemia. So just to finish, how much magnesium should we feed to the cows, right? So the NRC was providing, like I said before, some recommendations, but they ignored that the digestibility of magnesium is reduced by 7.5% for every 1% increase in potassium in the diet. So if we actually increase 1% potassium in our diet, we have to increase 4 grams per day the amount of magnesium that we provide to these dry cows. This is just an example. And NRC 2001 was not considering this. That's why I spent some time explaining you why magnesium is absorbed, because once you know that, then you can decide how much magnesium you have to fit into your diet. What's the target? Okay, so we have to be aware that you need to provide about 8 grams per day of absorbable magnesium to the cow, okay? So you have to multiply this by 0.25 if you want to convert it to magnesium in the diet, okay? Because the absorption is about 25, okay, %. So only 25% of what you feed will be absorbed. So if you need 8 grams, you have to do 8 grams divided by 0.25. Let me see how much that will be. 8 divided by 0.25. You're talking about 32 grams just for maintenance. Then you're going to provide 0.1 grams per kilo of milk. The previous NRC was using 0.15. That was the highest reported levels of magnesium. The average is 0.1, but of course that depends on the diet. The more you feed, the more magnesium you feed in the diet, the more magnesium you have in the milk. But 0.11 is a good average. For pregnancy, you need 0.3 grams per day. And for calves and heifers, and also primivorous cows, you need about 0.45 grams per kilo of average daily gain. So you put this together, and that's basically the percentage of magnesium that you need in the diet. So for weaning, you need 0.15. As a heifer, 0.12. It goes down because these animals eat a bit more. In dry, 0.12. Lactating, 0.20. Okay. If you're going to use magnesium oxide in the diet, how can you achieve that? Those are the levels. So you're going to feed 0.25 magnesium, 0.30, 0.30, 0.35% magnesium oxide. That would be the carrier. Keep in mind that this has about 60% magnesium. Would that work? Well, that's the general recommendation. That's why I spent a lot of time explaining how magnesium is absorbed, because it doesn't always work, right? Imagine we have a cow producing 40 kilos of milk, consuming 70 grams of magnesium oxide, with a diet that has 1.5% instead of 1.3% or 1% potassium. That means that the cow is absorbing 11 grams per day, okay? 42 out of the 70, that's 26% absorption. So 42 is 70 times 0.6. And then I'm going to convert this into the absorption. So it's only 11 grams. How much a cow producing 40 kilos needs? Well, she needs 8 grams for maintenance, and she needs 4.5 grams for milk. So I'm short, okay? I needed 12.5. I'm short 1.5 grams if I follow these recommendations, right? Why? Because I have a little bit too much potassium. So that's why I'm giving you these recommendations here, but just keep in mind that they're not fixed. They depend on the diet. It depends on the sodium. It depends on the fat. It depends on the potassium, the pH of the diet, and several other things. The last one, is it good for milk production? Well, if you look in the literature, there is no data, all right? The only study I could find associating milk production with level of magnesium is a very old study with cows producing 37 liters. So it's quite good for that age. So it's in 1982. These guys show that a diet with only 24% magnesium, the cows were producing 30 kilos of milk. Once they fed 64%, 0.6%, sorry, magnesium, milk production was highest. There is about 6 or 5 liter difference. So I think we need to do more research on the levels of magnesium that we feed to the cows and see if we can obtain a response to milk production. But like I said, there is not much evidence in the literature because there are no studies. People have not studied this. And the last one, is an excess of magnesium dangerous? Yes, it can be, but it's also a very safe mineral. Okay, you can feed more than 1% of magnesium in the diet, so it would be a lot of magnesium. We're talking about 200 or 250 grams. The first sign that you're going to see is diarrhea, and followed by a milk production reduction, and also the reduction in intake. At the moment that you remove magnesium from the diet, this is very reversible, and within 2 weeks, the animals return to normality. Okay, but again, it's very unlikely that you're going to feed that much. And if you do, it's not a huge problem. You'll see it right away and you can correct it. And with this, I think I'm done. I thank you for your attention, and I'm sorry if I took a bit too long, but I think the topic deserved going to the details.
Thank you, Alex. Very nice presentation. I think it was very technical, and it's good to see how many things are linked to magnesium. Thanks everyone for the questions and for what you said in the chat. So it's good to see that we have more than 15 different countries attending here the webinar. So it's quite interesting. I've noted the different topics also you were interested in when talking about magnesium, and I think Alex, you covered most of them. So talking about bioavailability, milk production, you mentioned it, heat stress also, and for your information, for the people attending this webinar, the previous webinar was also on heat stress. So if you want to have maybe more information about that topic especially, you can watch the last webinar in replay. And calving preparation, so you also talked about it, Alex. There was also a question regarding milk fats. Alex, what do you think? I know it's a bit like milk production. It's quite complicated. We don't have a lot of publication today, but what do you think?
Yeah, I've experienced in one farm, we had a problem with chronic milk fat. So we tested 1,000 things. We put in the amino acids because methionine may increase milk fat. We tested some buffers, and we actually look at the magnesium, and we increased the amount of magnesium in the diet, and butterfat went up a little bit. So that's the only case that that I encountered in a practical scenario where actually magnesium increased butterfat. So it's something to consider. In some occasions, if you have very low levels of magnesium, you may have a low butterfat in your cows. That's an extreme. So mean low, in this case, the ration had like 0.18% magnesium. So it was not very low, but it was low. Okay. And then we increase it to 0.25% magnesium, total magnesium, and not magnesium oxide. And we saw a response.
Okay. Yeah. And what kind of mechanism do you think is
causing that?
Here, yeah.
Well, it's like I said, it's the carboxyl. What's the name of it? I forgot. It's the enzyme that puts the fatty acids next to the other one. It's acetyl-CoA carboxylase. Okay. So that's what builds. So as you know, the fat in the mammary gland comes from two sources. You have the below 16C and above 16C. So above 16C, they come from the diet and body fat mobilization. Below 16C, they're just built from butyrate and acetate. So the enzyme that puts these things together, adding carbons and making fat, is depending on magnesium. If there is no magnesium or a little magnesium available, this enzyme cannot work.
Okay, thank you. Maybe just one another question. Someone asked about the citric acid test. So I don't know really about what, but I think it's linked to how to choose the magnesium source. I know we already talked about it, and it's not that easy. A lot of people also use the vinegar test, for example. what do you think about that, and what would be your advice?
Yeah, that's what I said a little bit in the presentation, right? So we use the vinegar test or the citric acid test. These tests, they always have an excessively low pH. So that makes all the magnesium oxides that you test better than what they actually are, okay? Because the lower the pH, the more the solubility. You want to test the quality of your magnesium oxide at a pH that is close to the rumen. And you can use buffers. You can use liquid rumen, artificial liquid rumens to do that. That would be my advice. I would not. I mean, citric acid or citric acid is better than nothing. Okay, but you just need to be aware that it's difficult to find differences, because the good guys will be very soluble. The bad guys will also be very soluble. But then if the pH goes up, these bad guys, they might not be so soluble. So that's a problem.
Yeah, so yeah, I can't say better. Thank you, Alex. If there is any other question, do not hesitate still to ask them in the chat. I will continue with the presentation to talk more about magnesium oxide and the specificities of pHix-up. So let me just share my screen. And if there is any other upcoming questions, we will try to reply to them at the end here or later. We will send you a complete summary Q&A answer document. So don't worry, everything will be replied. So talking about magnesium in general. So Alex already said a lot of things about it. I will go deeper on magnesium sources and where magnesium is coming from and how we produce magnesium oxide. So magnesium, we have it in the Earth's crust, of course, okay? It's the fourth most common element that we find after iron, oxygen, and silica. And we find it also, as you know, in the sea globally. So it's the third most common element in the sea after sodium and chloride. So it's really an element that you find everywhere. Chemically speaking, it's an atom, okay, and it's not possible to have a magnesium that is stable alone. So either it's Mg2+, okay, the ion that is absorbed by the cow, or it's in form of salts. And Alex talked a bit about it. You have organic salts that are not very used in ruminants nutrition. And you have inorganic salts, so magnesium oxide, the most known, magnesium carbonate, magnesium sulfate, magnesium chloride, etc. All of these salts, they have specific characteristics. And if we look at those salts, we need to look at, on one side, the bioavailability, okay? So here it's presented as a relative biological value based on magnesium oxide reagent grade. So the salt that is considered to have the highest bioavailability, and the magnesium content. So if I take, for example, magnesium chloride, okay, we know that magnesium chloride has a very high bioavailability, very high solubility and bioavailability. But the problem with magnesium chloride is that you don't have a high level of magnesium inside the product. So if I take 100 grams of magnesium chloride, you have 12 grams of magnesium, okay? 12% of magnesium, 12 grams of magnesium. And on these 12 grams of magnesium, you have close to 90% that is considered to be bioavailable, if we take this example here, which make 11 grams of magnesium solubilized. If I do the same calculation with magnesium oxide, let's take the one in the granular form. So it's less soluble when it's granular. For magnesium oxide, you have here 52% of magnesium in the magnesium oxide. And for the granular form, you have 60% of this magnesium that is bioavailable. So again, I take 100 grams, I have 52 grams of magnesium, and on these 52 grams, you have 31 grams that is considered to be solubilized, absorbed. We will come back on the definitions after. Here, making magnesium oxide as the product with the highest capacity to bring magnesium to the ration, but then you have the variability between the different magnesium oxides. So talking about this variability, and this is, I think, the most important when we talk about how magnesium oxide is produced. So most of you, I think you know, if you look at the picture on the right, on the top right, you have magnesium carbonate, you heat it inside a kiln, a rotary kiln, for example, and when it's heated, you lose CO2. And if you take MgCO3, you remove CO2, at the end, you have MgO. Okay, up to this, it's, let's say, easy. But then you have a question of temperature. Magnesium carbonate starts to lose its CO2 starting at 600 degrees. Okay, so if you look at the picture here, you can imagine the rock, okay, of magnesium carbonate. The CO2 is inside the rock and it wants to go out. So to go out, it will create its way. So it will increase the porosity of the mineral. So if you look at this picture here, you can see that there is some porosity because the CO2 went out of the rock. So as you are increasing the temperature, the CO2 is going out, and for animal nutrition, we want to reach a peak here of solubility, where the magnesium oxide has the highest porosity and then the highest solubility, reactivity, so the best for the animal. And this peak, it depends on the magnesium carbonate you have. So maybe you have a magnesium carbonate from Brazil, maybe a magnesium carbonate from Spain. The peak, the temperature for this peak will be different. Maybe in Spain it will be 800 degrees, maybe in Brazil it will be 900 degrees. So you need to select the right temperature to optimize the solubility of your magnesium oxide. This being said, if you continue to heat, so let's say, for example, 1200 degrees, then you start to lose solubility. So it's less useful for animal nutrition, for ruminant nutrition. It's used for different type of production, for example, industry, water treatment, desulfurization for the boats. And if you continue again to heat up to 1600 degrees, up to 2000 degrees, this will happen. So all the small things that you see on the picture here, small particles, they will start to get bigger and bigger and to take space in the mineral. And you lose the porosity. So if you look at this here, you can see that you don't have any space between the particles, meaning that you don't have any solubility. And it's what we are calling dead burn magnesia. So this product has no solubility. It's no interest for animal nutrition, but it's used, for example, for the steel industry to protect the kiln from high temperature. So here what we are interested in is really this part here, with magnesium carbonate heated at, let's say, 800 up to 100 degrees, with a chosen temperature to have the highest solubility. Now, knowing this, how pHix-up was built is really linked to this, graph. So knowing that each temperature of calcination will impact the solubility of the mineral, pHix-up was made from a blend of different chemical structure of the magnesium oxide to have an action on the short term up to the next meal. So with a picture of it, you can imagine a staircase. So on the first step, you will have a first structure of the magnesium oxide that is very soluble, very reactive, and will have a fast action, ultra fast action on pH. But then once this one acted on pH, it's done. So you want to use another source. So a second one will act on a second step. and once this second one has act, you have a third one, then a third one, a fourth one, then a fifth one, and then up to the 8 meal. So the idea here is really to have a fast action after the feeding and a long-lasting action, a maintained pH up to the next meal. I hope it's clear with this picture. So for the pHix-up concepts, we started with the morphology of the magnesium mineral, okay? So the magnesium carbonate, it has a specific structure and it's linked to some impurities. And these two depends on the location. So it's what I was saying. If you have a magnesium oxide coming from Brazil or magnesium oxide coming from Greece, China, whatever, the magnesium carbonate is not the same. Sometimes inside it you will have silica, sometimes you will have iron, and it will change the characteristics of the end product, so the magnesium oxide. When we have the location, so now you remember this graph, we look for the highest solubility of the magnesium mineral, the magnesium carbonate. So when we know the location, we have an idea of what kind of temperature of calcination we will use. And it makes magnesium oxide into specific chemical structure, okay? And this is the chemical properties of pHix-up. Now that we know this, we also want to act a bit on the particle size of the product, because we know that when you have bigger particle size, the action will be a bit slower, a bit longer on on solubility. The bigger particles, they take more time to solubilize, so more time to act, and the finest, they will be quicker to solubilize, so fast action. At the top here, you have microscope photo of a classic magnesium oxide, MgO 0.05 millimeters. Okay, so you can see it's only big particles. And then you have a photo of the microscope of pHix-up, okay? And you can see here you have very, very fine particles, and you have also bigger particles. So then it's also help to have this action, so same as the staircase, okay? You have on one side the fast action and on the other side the long-lasting action. So we are using both chemical properties and physical properties of the product. Now, okay, it's interesting. It's very a lot of chemistry and industrial aspects, I would say. If we talk a bit more about, okay, what is the interest to use pHix-up then? If it's a better magnesium oxide, or if it's a blend and having different action on solubility and pH. To have a simpler graph maybe than when Alex showed you, it's the same, but just a lot easier. When we talk about a product that is going into the rumen, the first thing you want is to solubilize it. So let's say this big thing here, brown thing, is magnesium oxide, and the red dot inside it is magnesium. If the magnesium oxide is not solubilized, this red dot, this magnesium, won't be absorbed. It's not possible. So you need first to have the solubilization of the magnesium, so the green dot, and then this green dot will be absorbed through the way that Alex presented. So it's going to the blood, and then in the blood, it will go to the liver and to the different organs to be used by the cow. So it's a bioavailable nutrient. So here we make really the difference between solubility and absorption. And today we are easily able to talk about the solubility of magnesium oxide, because we were able to measure it in rumen juice. But measuring the absorption is more complicated, because you need to use, of course, in vivo animals. And we are currently trying to work on a study on this to have more information about the true absorption of magnesium coming from different magnesium oxide source, more or less soluble. So knowing this, this is a graph coming from a rumen juice, okay? So trying to be as close as possible to the rumen condition. We talk a bit about the test, citric acid test or vinegar test. So here it's not in vivo, it's not in the animal, but we are as close as possible to the real condition. And you can see that we have tested different kind of magnesium oxide, but with similar particle size. So from MgO-A to MgO-F, you can see particle size are quite similar, but you have a strong difference in terms of solubility and effect on pH. So if I compare, for example, MgO-A and MgO-F, you can see that MgO-A has a higher effect on pH, okay, increasing it from 5.8 to 6.3. MgO-F is increasing pH from 5.8 to 5.9, so almost no effect. And you have a strong correlation with the solubility. So MgO-A, which has the highest effect on pH, it has also the highest solubility of the magnesium. So if I take 100 grams of MgO-A, I have around 22 grams of magnesium solubilized. But if I do the same with MgO-F, I have only 14 grams of magnesium solubilized. So it's very important to take into consideration also this specificity of each magnesium oxide. And if you take only one magnesium oxide, you don't know what would be the true effect on pH and on solubility. And then you have pHix-up, okay, with after 2 hours the highest effects on pH, and we know that it's maintained over time. And on the other side, after 6 hours, the highest solubility also. So you combine, if you remember the staircase, okay, you combine the fast action and then also the long-lasting action. So on one side, you have an effect, a regular effect, stabilized effect on pH, and you are also bringing magnesium regularly to the cow. Okay, so this is in vitro. What I wanted also to show you is an in vivo results in vivo studies. So here are trials that we've done in France, comparing 200 grams of sodium bicarbonate and 50 grams of magnesium oxide with 85 grams of pHix-up. So for those of you that knows well pHix-up, we have here we remove total substitution of sodium bicarbonate to use pHix-up. So we have the exact same neutralizing capacity. We expect to have at least exactly the same action on pH in the cow. And here you have some information about the composition of the ration. Okay, so 41% of concentrates. We are in France, so for those of you in Middle East or in Pakistan, for example, or India, you have a maybe low level of concentrate for you. But it gives an idea, and the average starch level was 26.5%. As you can see here, the pH was the same, so it's what we are expecting. Now, the thing I don't show here is the variation of pH during the day, and what we want to do is to stabilize as much as we can the pH, and we proved in some studies that indeed with pHix-up you have a pH that is more stable. And in that study, and it was also proven through a recent meta-analysis, we have an improvement of the milk production. So linked to all of what we talked about today, for pHix-up, the main effect, what we are waiting from the product is mostly to act on pH. And the effect here we can observe on milk production is maybe more linked to the effect we have on pH, but it's maybe linked also to the magnesium that you bring through pHix-up, and especially regarding the fat content. So we know that today there is no big proof that there is a link between magnesium and milk and magnesium and fat content. But in most of our studies, we observe that we have a maintained fat despite an increased milk yield. So we don't have a dilution effect, meaning that the quantity of fat produced per cow per day is higher with pHix-up compared to the previous buffer solution that was used. And the same for protein, but with a less important effect. And yeah, as I was saying, we have a very nice meta-analysis actually that was presented last week in ADSA in the US, showing approximately the same results. So if you're interested about this, do not hesitate to ask us. And very quickly, because I see the time running very fast, I wanted to show you some recommendation of the use of pHix-up. Okay, I already presented this in the last webinar, so the idea is a bit the same. So you have an initial situation, for example, with 250 grams of sodium bicarbonate, 50 grams of salt, 100 grams of calcium carbonate, and 50 grams of magnesium oxide. We will look at the neutralizing capacity and the different level of minerals only bring by the minerals that are mentioned here. Okay, what is written here, it's not the total mineral of the ration, it's only with the minerals that are on the slide. So the first option would be to remove entirely sodium bicarbonate. And we know that in some situations it's possible to do that. So here I remove entirely sodium bicarbonate. I increased a bit salt, okay, to increase the sodium level, to keep a bit the sodium level. And I put 100 grams of pHix-up. We have exactly the same neutralizing capacity. We increase magnesium. We decrease sodium, of course. And then the chloride is a bit increased through the salt, okay? So this is the first option. Here I will be very careful in the ration, for example, in Middle East, where you have a very low amount of sodium in the basic ration. But yeah, if you have enough sodium in the basic ration, you can remove entirely sodium bicarbonate, and we did this a lot of time without any issue, and even good results on the performances. So it's possible to do it that way. The other possibility is to keep a bit of sodium bicarbonate to maintain also the sodium level, but without increasing salt and without increasing the chloride level. So this is the second possibility, using 85 grams of sodium bicarbonate and 70 grams of pHix-up. So kind of a balance, and here you have again the same neutralizing capacity. And then we advise, of course, to adapt the pHix-up dosage according to the period. So if there is a heat stress, we talked about it last time. If it's during the dry period, you can also bring pHix-up. For a period with a stress, for example, the silo change or whatever other stress period, it's possible to adapt the pHix-up and sodium bicarbonate dosage. So that's all on my side. So thank you very much for your attention. I just wanted to remind, so I saw in the chat someone asking the question. So of course, this webinar will be available on replay. So you will be, it will be possible for you to check it again after if you want. You can already save the date because our next webinar will be on acidosis, the 9th of September. So I'm sure that you will be again very plenty of you attending this webinar. Before leaving, I just want to check quickly if there is some questions, important question about pHix-up. So I saw there was a question, for example, if pHix-up can be used in combination with some calcium supplements to be best absorbed by dairy cows. So I don't know if you mentioned any interaction with calcium, Alex, but what I have in mind, and you can confirm, is that when you have high level of calcium, it may reduce a bit the magnesium absorption. So I would say no, bringing any calcium supplement won't help the magnesium absorption, but it's less important, the effect is less important than, for example, when you have potassium and magnesium, and potassium will really reduce the magnesium absorption. I don't know, Alex, if you have any elements regarding the link interaction between calcium and magnesium absorption.
No, I agree. We don't know why, but all we know is that if you feed lots of calcium, magnesium absorption will go down. So, but we don't know the mechanism by which that happens.
Okay. Then I saw a question, is the buffering capacity of magnesium source important? So I would say yes, but as described during the presentation, you have a huge variability between the sources. So you can say maybe one magnesium oxide will have a very high effect on pH, but then maybe too high, too fast, too quick, but not on the long term. And on the opposite, you may have some sources with very low action and not enough powerful to act on the short term, but maybe acting on the long term. So it's important to keep in mind this variability between the different magnesium oxides. Can we increase the dose of magnesium oxide in case of high humidity? Good question. I would say it's linked also to the temperature. I'm taking into account temperature and humidity index. So it's a bit also what Alex said and what we talked about in the previous webinar. So yes, if you have an increase of the temperature and humidity index, it could be interesting, to increase a bit the magnesium level, because you have a risk of a decrease in the magnesium absorption. And there was a question, okay, by using pHix-up, should we replace yeast, and as they are maintaining ambient rumen pH? So again, Alex, you can complete what I say, maybe talking about buffer generally, but for me, yeast and buffers are not acting the same. So buffers and pHix-up will act directly on pH, okay? So the action is to increase the pH directly, it's acting on pH. Yeast, it's an indirect action. So it will help the bacteria to digest the fiber, but for that, you need to have bacteria. So you need to have a right rumen environment, okay, a good rumen environment. So using both is, I think, good, because you have a kind of complementary action, but I don't know, Alex, what do you think about this?
I agree. The mode of actions are very different from one and the other, and they're complementary. So yeah, if you have the space in the diet and the resources to use both, both is better. Yeah.
Okay.
But one does not substitute the other.
Yeah. And I have another question, and I will need your help also, Alex, is how does the drinking water or the water quality may act on magnesium absorption or magnesium bioavailability?
Yeah, well, if you have a very hard water with lots of calcium, you may have a little problem, but it's very unlikely. So I would say that the mineral content of the water is not going to have a huge influence on micro minerals. It might have some interference with micro, with zinc and with iron and stuff, not with magnesium. I wouldn't worry about it.
Okay, perfect. For all the other questions, so don't worry, we will check everything and we will make sure to reply to all the questions and send you a Q&A summary. So thank you very much to all the people that attend the webinar, and thank you, Alex, for this nice presentation. It was, I think, very interesting.
Thank you. And thank you for listening.
Thank you, everyone. Bye.
Bye-bye.